Welcome to a review of exponential functions. So these are topics that we have covered in the past, but this is the beginning of the this topic that we're looking at, which will lead into logarithms. But we're just going to have a quick look at some of the content that you've learnt before, maybe introduce some new content. But those four dot points are where we're heading towards. So with the exponential function, reminder that, when you differentiate the exponential, you get the exponential back itself. So it's its own derivative. Y equals 0 is the horizontal asymptote. 1 to 1 is the function type, and it's always increasing, meaning our tangents are always positive. One of the rules that we learned was you can change an exponential into a logarithm or a logarithm back into an exponential. So just remember those that rule because it does become handy, in particular when we start to look at integration or even differentiation at times and solving exponentials or logs. So here's our first one. We're going to solve a exponential that's in the form, or looks like it's in the form, of a quadratic. So when we solve this, we rewrite e to the 2x. So we use our rule with indices, and that is that anything raised to its power, you multiply the powers. So we can do the opposite. So we can take the 2x and rewrite it as e to the x all squared. You can see now that that is definitely in a quadratic form. Adds to give the middle, multiplies to give the end when we're doing that, or PSF if you want to use PSF. So factorising that into two brackets. So you get -4 and -1 are your brackets. Multiplies to give +4, that's -4 and -1. Adds to give -5, that's -4, -1. So that's our two brackets. Solving it, that's e to the x equals 4 or e to the x equals 1, just like we solve any normal quadratic. And to solve it, we use our rule. So if it's e to the x equals 4, we change that. So x equals log base e. So remember, if it's a base e to the x, your solution becomes log base e to the 4 and log base e to the 1. And log base e can be written as ln. And if you type in on your calculator log base e of 1, you get 0. So a reminder with the on the formula sheet, differentiating an exponential. So if it's e to the f of x, you put f dash of x out the front and you do e to the f of x. Do not touch that function that's up the top. So here we go. We've got two examples that we're going to have a look at. So e to the x squared plus 3x and x squared e to the 3x. So the first one, e to the x squared plus 3x. So we take the function that's up the top, x squared plus 3x, we differentiate that, which gets us 2x plus 3, and we put it out the front. So you get 2x plus 3 outside of e to the x squared plus 3x. With the second one, hopefully you can see that it's a product rule. If you've seen that, fantastic. Let's go ahead and do it. So the product rule, u equals x squared and its derivative is 2x, and v equals e to the 3x. So you take the function, the 3x, and you put the differential of that out the front, 3e to the 3x. Use our product rule, uv dash plus vu dash. Now that would be a perfect solution, but we do know that we are trying to factorise. So out of x squared times 3e to the 3x plus e to the 3x times 2x, hopefully you can see that a common factor out of that is the x, and a common factor is e to the 3x. And so you take x, e to the 3x outside of 3x plus 2. Some of the applications, finding gradients or equations with our tangents, normals, stationary, concavity, curve sketching, max min, all of the things that we've done in the past. So we're just going to look at a couple of examples that apply. So our first example is find the equation of the normal to the curve y equals e to the 2x when x equals 0. Equation of the normal. So let's break this down. Equation y minus y1 equals mx minus x1. Equation of a normal, it's a straight line. So we use the straight line formula. The normal, so hopefully you remember that the normal is the perpendicular to the tangent. So gradient of the tangent from dy dx and then multiply to get -1. The negative reciprocal is how some of you might remember it. X equals 0. Remember, for every x value you need a y value. So therefore, we need to sub that x equals 0 into our original equation. So let's work through this. So we're going to do the x equals 0 part first. We're going to find the y value by substituting the x value, because we're going to need that anyway. So let's do that as our. So we sub 0 in to find the y. E to the 0 is 1. So our coordinates are 0, 1. That's going to be helpful when we find the equation, because remember, you need a set of points. Next, we're going to find the gradient of the tangent, because if we want to find the gradient of the normal, we need the tangent first. And to find that, you differentiate. So differentiating that, you get 2e to the 2x. Substituting 0 in for x, you get the gradient of the tangent is 2. Remember, to find the gradient of the normal, negative reciprocal. So therefore, the gradient of the normal is equal to -1/2. Substituting that in to find the equation, you get y equals -1/2x plus 1. That's our solution. Or if you then want to rechange that into general form, multiply by the 2, make the x positive, and you get x plus 2y minus 2 equals 0. Example 2, finding the stationary points. Stationary points when the first derivative equals to 0. Points means you need an x and a y. So differentiating x squared e to the 3x, this was the one we did earlier, so I've just copied that to here. All right, and that's the product rule. So remember, you would have to use a product rule. In this case, if you don't factorize, you're not going to get the solutions. So where I said in the previous example that, you know, having used the product rule and substituting in, you would be fine. If you don't factorize, you can't solve this. This is those one-off examples. So now we can actually go and solve it equal to 0 to find the stationary. So our first one is when x equals 0. Our second one is when e to the 3x equals 0. And the third one is when 3x plus 2 equals to 0. Note, an exponential never equals to 0 because it approaches the x-axis but doesn't actually touch. So it's not a solution. So we're only solution the other two, x equals 0 and x equals -2/3. Substitute both of those points back in, and so you get your values for the stationary points. Integration. So the integration uses the rule that if you've got the derivative out the front, then you go back to the exponential. This is on your formula sheet. So integral of 6x e to the x squared, and evaluate the integral of 0 to 1 of e to the 4x. So with 6x e to the x squared, so if I differentiate x squared, I get 2x. So that means I need 2x out the front, but I've got 6x, and 6x is 3 lots of 2x. So I want the 2x, so I take the 3 out the front. So now I've got 3 lots of e to the x squared. That's using our integration formula from our formula sheet. When I want to do the integral from 0 to 1 of e to the 4x, so I need a 4 out the front because the derivative of 4x is 4. So I need a 4 out the front, and a quarter times 4 gives me 1. So therefore, when I integrate, I get a quarter e to the 4x. Subbing in 1 and 0, I get a quarter e to the 4 minus a quarter. All right, one application. Some of the applications, remember, is like finding the area between two curves, finding the primitive, calculating the value of the constant. So we'll just have a look at examples. Example 1, Given f dash of x equals 2 plus 3e to the x, and f of 0 equals 4, find f of x. So we've got f dash of x, so we're going to integrate. So f dash of x, integrate and add c. So when we integrate 2 plus 3e to the x, the 2 goes to 2x, and the 3e to the x stays as is, and then you put a plus c on the end. So now we substitute in the values from f of 0 equals 4. So when x equals 0, f of x equals 4. So putting those in, 4 equals 2, lots of 0 plus 3e to the gets you 4 equals 3 plus c, so c equals 1. Go back to our equation, so that means that f of x is 2x plus 3e to the x plus 1. Second example, find the area between the curve y equals e to the x equals 0 and x equals l. So there's an example. Oh, there's how it looks. That's the exponential curve cut off from 0 to ln4. So that means we're integrating from 0 to ln4 e to the x. The area is above the x-axis, so it's positive. So I don't need to take any other consideration. E to the x integrates to e to the x, and then I substitute ln 0. So I get e to the ln4 minus e to the 0. If you're not sure what e to the ln4 becomes, type that in on your calculator. Type in e to the power of and then put ln4 there. You actually get 4, and then minus 1 gets us 3 units squared. Thank you very much.